I want to make sure it really is recording. There are only 2 problems in this lesson, but one of those 2 problems has 4 steps. So still take a certain amount of time to cover, but not a whole lot. Okay, let's get the old screen share going. Okay, so this lesson pretty much continues where other lessons left off. That we're taking into account all the information that we can obtain about a function from its first and second derivative that would enable us to draw a graph of a function. Although you won't actually be drawing a graph. There is one problem where several possible graphs will be presented to you for a multiple choice question, and you need to use your knowledge of a derivative to pick out the right one. And that's actually what this first problem is about. What does the first derivative and second derivative tell us? For example, the first derivative, if it's positive, a function is increasing. If it's negative, it's decreasing. If the second derivative is positive, a function is concave up, otherwise concave down, and so on. So here we have, for his first problem, we have a function f of x. We're not given a formula for a function. We're just given these facts about it. We're given its value at x equal 4. We're given a value of its derivative at x equal 4. And we're also told where a function has a positive and negative first derivative. And also we're told that the second derivative is always negative. So what you're told about the sign of the first and second derivative gives us an idea of what the graph ought to look like. So I'm going to show you some graphs, but before getting to that, let's interpret these things. Okay, so each one of these 5 conditions tells us something about the graph. First, we have this point. Great, can't type today. X equal 4, y equals -3 lies in the graph. So if you're presented several graphs, you want to look for that point, make sure it's on it. Otherwise, you can forget, you can eliminate that choice. Second, because a derivative at x equals 4 is equal to 0, what we can say is that the graph has a horizontal tangent line at x equal 4. Another way of interpreting that informally, the graph is flat at x equal 4. It may mean a max or a minimum. We don't know that yet, but we will be able to tell from the other conditions. But the graph has a slope of 0 at x equals 4, because that's what the derivative means. It's a slope of a curve or a slope of a tangent line at that point. Okay. The third condition tells us that f is increasing for x less than 4. So because its derivative is positive there, that is similarly the next condition, the fourth condition, tells us that f is decreasing for x greater than 4. Now, these 2 conditions together tell us something. So if you have a function that is increasing up until a certain point and then decreasing, then that is a local maximum. So when the sign derivative changes from positive to negative, that's a local max. If it goes from negative to positive, that's a local min. All right, so we have a previous condition. So these 2 conditions together say f has a local maximum at x equal 4. Okay. So that's one thing to look for in a graph. And then finally, f double prime being negative everywhere. That tells us the graph of f is concave down. Okay. There are no inflection points. All right. So now what we could do is use this information to look at 4 graphs and pick out the right one. So make sure. Okay, need to zoom out a bit to make sure that all 4 graphs can be seen. Oh, okay. I need to move us to a new page. Okay, so I'll zoom out a little more. Okay, so so which one of these 4 graphs is it? So if a point x equal 4, y equals -3 must lie in the graph. It has to have a local maximum at x equal 4. The graph has to be concave down. So the 4 graphs, A, B, C, D, which is the correct one?
D.
Yes, it's D. All these other graphs, A, B, and C, all 3 of them, the function is concave up. Only this one is concave down. Now that condition alone would have been enough, but just to point out the other things, like these A and B do not have the graph. They don't have a red point on the graph. So at x equal 4 and y equal -3, that's this point right here where my mouse is not even on graphs A or B, so they're eliminated for that reason. All B, C, and D have a horizontal tangent at x equal 4, but this one is not the right point. But yeah, that's sort of later conditions of going from increasing and being concave down. Only this graph satisfies this condition. So you could use individual conditions on the graph. I had 5 conditions, but it turned out not all of them were even needed. But you can use these conditions to eliminate certain graphs right away and narrow it down to the right one. So look for concavity, increasing versus decreasing, whether a certain point is on the graph, things like that. Okay. Questions about this one? Now, for the second, and believe it or not, last problem in this lesson. So we have actually, and let me zoom in now. Okay, so here we're given a formula for a function, and we're asked to gather certain piece of information about it. Where is it increasing, decreasing? Where is it concave up, concave down? These follow from the first and second derivatives, respectively, that you need to obtain in the first part. And you give intervals like you've done in previous lessons. And then from this information, increasing or decreasing, concave up, concave down, you can determine wherever any local minima, maxima, and inflection points. So Minima and maxima happen when there's a change in the function from increasing to decreasing. Inflection points happen where there's a change of sign in the second derivative. All right. So for the first step, it's just taking a derivative twice. So this is one of the easier functions you've had to deal with, where you're just using the power rule. So there's f of x again. Rule. Here you're bringing down the 4, deducting 1 from the exponent for that term. Here you're just using a coefficient rule. Plus 1, that has a derivative of 0, so it goes away. So then if you clean up the first derivative, all right, so 2x cubed plus 128. And then you take the derivative of that to get the second derivative, and it's just going to be power rule again. So we'll get 6x squared from here, and then we don't get anything from here. So now we have a derivative. We're going to use the first derivative to determine whether a function is increasing or decreasing. So first we have to find out where a derivative is equal to 0, because that would mark any possible sign changes. So if we go ahead and do that, so we set f prime equals 0. So then 2x cubed plus 128 is 0. So then we just go ahead and carry out the algebra here, and we're going to get x squared is minus 64. Now remember, whereas the square of a negative number is positive, the cube of a negative number is negative. So 64 happens to be a perfect cube because 4 cubed is equal to 64. But because it's minus 64, our cube root is going to be minus 4. So that would be the only solution. That's the only point at which f prime is equal to 0. So then to check increasing versus decreasing, we need to pick points on either side of minus 4 and see where a derivative is positive or negative there. So this one critical point, minus 4, divides the real number line into two pieces. And on those two pieces, it's going to be either all increasing or all decreasing. So for x less than minus 4, we can pick anything, as you've seen in previous problems. So for convenience, just pick something like minus 10. So then we get a very large negative number here. We're going to get minus 2,000 because, as I said before, the cube of a negative number is negative. And the plus 128 is definitely not going to offset that. So minus 1872. So f is decreasing to the left of minus 4. But now we need to look at x greater than minus 4. And again, you can pick anything. And it could be convenient to pick up, well, actually, here we can just pick 0. So we just get 128 in that case. Sometimes it can be convenient to pick numbers that are like negatives of one another if they put you in different intervals. But here we can just go ahead and pick 0, and we get a positive value. So f is increasing to the right of minus 4. So now we can state the conclusions. So wherever Hawks asked if the function is increasing, this is the interval. So from minus 4 off to infinity. So for x greater than minus 4. And then because we got a negative value here, it's decreasing from minus infinity up to minus 4. Now, the next step is going to be the exact same process, only applied to the second derivative to determine concave up versus concave down. So concave up or upward if its second derivative is positive, concave down if it's negative. So we have the second derivative from before. So we need to see where that is equal to 0. Well, the second derivative obtained in the first step was 6x squared. But that just means that x is 0. That's the only possibility there. So now we just check if we need to check one positive and one negative value of x. So this could be where it's a good idea to check values that are just negatives of each other. Just randomly picking an x value that's negative, just pick minus 10. So we get a positive value there. And then we pick a positive x, so we just pick plus 10. So the algebra works out largely the same. In fact, we get the same result in this case because we're squaring, and we get plus 600 again. So, and we can see from the second derivative, 6x squared, that's never going to be negative. So you can, even without doing this, you can tell it's never going to be concave down. So we can conclude that's concave up everywhere. So the whole real number line. So the interval you would enter in Hawks is minus infinity to infinity. And then there's an answer box for concave down, and you would click the radio button for none. There are no intervals where it's concave down. So then the last thing to do, you've done all the calculus and algebra now, it's a matter of interpretation. From wherever a function is increasing or decreasing, we can determine if there's local max or local min. And then from any sign changes in the second derivative, we can identify inflection points. So there's only one critical point at minus 4. There are no endpoints. It's not one of those problems where you find the absolute maximum, and we're looking at local max and min. So for that, we look at sign changes in the first derivative. So from 2 steps ago, it was decreasing up until minus 4, and then increasing after that. So a function is decreasing, then increasing. So sign change from minus to plus, that is a local minimum at that point. All right, so minus to plus is a local minimum. Plus to minus, as was seen in an earlier problem, is a local maximum. And there are no inflection points because that requires a change in concavity from up to down or up, down to up. But the function is never concave down, so there's no opportunity for an inflection point. So to summarize, this is what we have. We have a local minimum. So Hawks has answer boxes for minimum, maximum, inflection points. So for these last two, local max and inflection point, you just click none, and then you would enter minus 4 as the next value in the answer box for local minimum. So you get the first and second derivative, use the first derivative to tell increasing versus decreasing, second derivative to tell concave up versus concave down. Sign changes in the first derivative reveal local maxima or minima. Sign changes in the second derivative, if any, reveal inflection points. So that's what this problem is all about. And knowing information about what happens at these essential points, where these things happen, would be helpful for drawing the graph of a function. You have a good idea from where it's increasing or decreasing or its concavity to see what kind of shape the curve should have and what key features it has. Okay, so questions about this problem? Okay. I will end the recording at this point. Anyone has any questions, I'll stick around. So lesson 4.4 coming up on Thursday.